Well, in the last couple of lectures, we have discussed the fundamentals of stereology, and I thought today I will discuss a little bit, or I will elaborate a little bit on grain size measurements, because as grain size measures are an important characteristic of microstructures, and they influence different properties of the material. So, I am going to talk about some grain size measures in this lecture to begin with. We saw in the last lecture one particular grain size measure which was called as the mean intercept length, and which as a symbol I have put it as L bar. And in this, what we do is, if you have a polycrystalline microstructure with grains and I want to get an average grain size out of this, I had put a grid of parallel lines on this and counted the number of intersections that these lines make with the grain boundaries. And from that we obtained a intersection count per unit length, SPL, which is n small n, the number of intersections that this grid of parallel lines that is made with the grain boundaries, divided by the total length of the grid. From that we got a mean intercept length of 1 upon PL. This is a very useful measure, and today a very commonly used measure of grain size. However, let us take a look at some of the other possible grain size measures that are used, and many of them, in fact particularly one of them is particularly used in industry. So, to begin with, let me also take another kind of measure which uses grain counting. So, the grain count method in the grain count method, you measure number of grains per unit area, NA, this is number per unit area. So, I will be counting these grains and then dividing it by the total area over which I have measured the count. If we can make the assumption that my grains in 3 dimensionals are spherical, okay, if they are close to the spherical shape, then I can relate the average area of a grain A bar to be equal to 2 by 3 pi r square, where r is the radius of the grain. So, and how can I get A bar, the average area of a grain? Well, I have already measured the number of grains per unit area, and hence A bar is nothing but 1 upon an A, because in a unit area if I measure so many grains, the reciprocal of that would give me the average area of a grain. Now, from this it is easy to go to the diameter of the grain. So, the size measure that I am using is the diameter. So, I come to the diameter of the grain, if I call that as D, is nothing but 2 times 3 by 2 A bar upon pi to power half. And this simple relationship for the grain diameter is really coming from right from here. I essentially get the radius from here multiplied by 2, this factor 2 that comes from there gives me an estimate of the, let us say, the average diameter of the grains, if we can assume that the grains are spherical in 3 dimensions. So, now I am able to relate the diameter to the experimental measure of number of grains per unit area. Here I had made the measure of the mean intercept length, and let us see, can I relate the diameter of grain to the mean intercept length if we make the assumption that the grains are spherical. Well, again there is another stereological relationship for the mean intercept length if the grains are spherical of radius r, and that is simply 4r divided by 3. Of course, I have not derived any of these relationships, but these are directly coming from the principles of stereology. From here, it is very clear that the average diameter of the grain in terms of the mean intercept length is nothing but 3 by 2 L bar. So, this is another grain size measure that I can convert the mean intercept length into a grain diameter if it is reasonable to assume that the grains are spherical. Now, there is third and final measure of grain size that I want to introduce today, and it is still used in industry quite a lot, is the ASTM grain size parameter. And I will use the symbol G, capital G for this. Now, what is this ASTM grain size parameter? Well, let me give you first the original definition of the ASTM grain size parameter, and let me write down a relationship with G, that n is equal to 2 to power G minus 1, where n is the number of grains visible in the microstructure per inch square. So, this is a very old definition, and that is how the measure of inch comes in, and this is measured at a magnification of 100x. So, we take the sample, put it in under a microscope, look at it at 100 magnification, and then put a mask on it, and to measure how many grains are there in 1 inch square. Now, of course, we can do this. However, we can also use this measure of NA, number of grains per unit area, at 1x. So, no, the magnification is taken into account, not 100x, 1000x, whatever, at simply 1x. What is the number of grains present? And I can, so it is essentially conversion of this formula to different units using NA, and one can write the ASTM grain size parameter in terms of NA as 3.3219 log to the base 10 NA minus 2.954, where units of NA are in per millimeter square. So, in 1 millimeter square I have so many grains, I put it in this relationship and I get the value of the ASTM grain size parameter. I can also relate the ASTM grain size parameter to the mean intercept length, and that is given by the relationship G equals minus 6.6439 log to the base 10 L bar minus 3.288, where the mean intercept length units are in millimeters. So, these are two relationships one can use to get a grain size measure in terms of the ASTM grain size parameter. One interesting thing that one should look at it, and one should look at this particular definition of ASTM grain size number, that as number of grains per unit area is increasing, your grain size parameter will increase. Now, what does this mean? So, larger values of G implies larger number of grains in a given area, which means the grains are smaller. So, larger is the grain size parameter G implies smaller are the grains. So, this is this should be noted, that large values of G implies small grains, small values of G implies large grains. Now, with this I will just conclude this, that these are some of the important grain size measures that I think you ought to be aware of. And then finally, in many of our stereological measurements, metallography measurements, we are measuring or counting grains, we are counting particles. So, we should have a good idea how to properly count grains or how to properly count particles, so that we get an unbiased estimate. And to do that, I will just briefly take you to a methodology for counting of polycrystalline grains, for example, to begin with, and then we will also have a look at a similar methodology for counting of particles. So, methodology of counting of polycrystalline grains, let us take a look at it. I have here a microstructure of a single phase polycrystalline material, and you can see the grain boundaries and the grains very clearly in this. So, what we do is we superimpose a counting mask. So, as you can see, this is my counting mask of dimension 219 micrometer times 246 micrometers. Within this mask, I am going to count grains in such a way that I get an unbiased count. Now, what is the problem at hand when we are counting grains? The problem is as follows, that grains which are completely inside can be counted as whole, but what do we do with the grains which intersect with the boundaries? How much or how big a part of that grain we count? So, this methodology describes a technique for counting, so that I get a statistically unbiased estimate. Now, you will notice in this mask that there are two sides of the mask have red line, and then I have the green line on the other two sides. The red line is considered as the forbidden zone. So, if a grain intersects a red line, we do not count it at all. If a grain intersects a green line, we count it as a whole grain. And of course, any grain which is not touching any of whether the green line or the red line of the mask, but is completely inside the mask, will be counted as a whole grain. So, here is my mask. So, for example, this grain intersects the red line. So, I have actually marked it as a red grain that I am not going to consider that in my count. Similarly, there is another red grain and yet another one, and here in fact this is a grain which intersects both the green and the red, but since it is intersecting the red, we will ignore in the count. So, all of these grains would be ignored in the count. Now, rest of the grains that are there we must count. So, for example, these grains which intersects only the green line will be counted. So, all of these grains are intersecting the green lines, the green line of the mask will be counted and they are marked as dark green. Then there are grains which are completely inside the mask, and these are marked as light green and they will be counted as whole, and so will be the rest of the grains. So, if I look at this count, I get number of complete grains inside the frame. So, these are the light green ones here, they are 60 in number. So, we will count them as 60. Number of grains in the inclusion region. So, the grains which are intersecting only the inclusion region, the green lines will be counted and they are numbered 20. Number of grains touching an exclusion region is the one where the red line of the mask is there, which are 14 and they are going to be ignored. So, the total grain count that I have, the effective number of grains in this mask are simply the first two numbers 60 and 20 and 14 will not be counted. So, I have 80 grains in this area, hence NA, the number of grains per unit area. I have only written here as N, but it is N sub A as I had put on the board, that these are the number of grains per unit area, which is nothing but 80 divided by the area of this mask, which is 246 into 219. Hence, this gives me the number of grains per micrometer square, it is 0.0015. Well, I can convert this into per millimeter square as well by multiplying it by a factor of 10 to power 6. So, what is the average area of a grain? As I had just stated on the board, the average area of grain is the reciprocal of the number of grains per unit area. So, it should be the reciprocal of 0.0015. If I take the reciprocal, the average grain area is nothing but of the order of 667 micrometer square. Now, I can use this to calculate my ASTM grain size, or if I assume my grains to be almost spherical, then I can get an idea of the grain diameter using this count. Now, a similar methodology can be used for counting of particles as well. These are isolated particles. For example, the microstructure that I show you here are the graphite nodules, and I want to have a count of the number of graphite nodules per unit area. Again, I put a mask on the microstructure of a red line, the forbidden zone, and the green line, which is the inclusion region. Again, all the particles which intersect the exclusion region, that is they intersect the red line of the mask, will not be counted. So, these are all particles which will not be counted. Similarly, I have these dark green particles which are intersecting the inclusion region will be counted, and as well as all the particles which are completely inside, which are not touching either of the exclusion or the inclusion region, will also be counted. So, if I look at this particular count, number of complete particles inside the frame, which are these light green ones, are 88 in number. Number of particles in the inclusion region are 7 in number. Number of particles that are touching an exclusion region are 14, and which will be ignored in the count. So, for example, this particular particle, even though it is at a corner, it is touching an inclusion zone, but it is also touching the exclusion region and hence will not be counted. So, the total number of particles that I have, effective number of particles inside the frame, are just the N1 plus N2 or 88 plus 7, and giving me a total count of 95. Number of particles per unit area hence is 95 divided by the area of this mask, which is this length 505 microns multiplied by 450 microns, giving me the number as 0.00042 per micrometer square. So, this was a simple process, a simple procedure for counting of grains and particles. With this, all my discussion regarding quantitative metallography is complete.